Right. So get this. Um, what if I told you that you could cut an apple in half, rearrange the pieces,
Okay.
and end up with like 2 whole apples? It sounds kind of crazy, right?
Yeah, like some magic trick.
Exactly. Well, today we're diving into this thing called the Sierpinski-Mazurkiewicz Paradox.
Okay.
And it's this like mathematical concept that says that this apple magic,
Yeah.
it might actually be possible,
Hmm.
at least on like a flat surface, a 2D plane.
Interesting.
And you sent over some really cool stuff about this, some
Yeah.
articles and stuff about set theory, even some historical background on it.
Right.
And I gotta say, my brain is already like starting to hurt a little bit thinking about all this.
It definitely bends your mind a little bit.
Yeah. Yeah.
It's a tough one.
So maybe we should
Yeah.
start slow, break it down a bit.
Right. Right.
So the sources are saying that you can take a set of points on a plane and you can divide them up into pieces.
Okay.
And then you reassemble them like a puzzle.
Yeah.
And you get 2 identical copies of the original set.
Right.
But we're not talking about stretching or distorting anything.
Oh.
The paradox, it's all about rigid motions,
Yes.
like just sliding and rotating pieces.
Exactly.
So that's where it gets kind of weird, right?
Absolutely.
Because at first you think, well, how could you,
Yeah.
double the area of something just by...
Right, just by moving the pieces around.
Yeah, exactly. It's like you're getting something for nothing,
Yeah.
which, usually doesn't happen.
Right. That doesn't quite work that way.
So the key here is that we're not talking about, shapes like squares and triangles.
Yeah.
These are sets of points that are infinitely intricate.
Yeah.
They're so detailed that you can't really measure them
Right.
in the normal way, like...
Yeah, it's not like you can pull out a ruler.
Exactly.
Yeah.
Exactly.
And measure it.
So it's kind of like, trying to measure the coastline of an island.
Yeah. Yeah, that's a good analogy.
You can get a rough estimate,
Right.
but the closer you look,
The more detail you see.
the more inlets and curves you find.
Yeah.
And it makes the coastline seem,
Much longer.
like way longer.
Yeah.
And these sets in the paradox, they're kind of like that.
Exactly. They're almost unmeasurable.
It's like trying to measure a cloud or something.
Yeah, that's a great way to put it.
It's always changing,
It's constantly shifting.
Okay, so then the question is, how do you even create these bizarre sets?
Right.
And the sources start talking about free groups.
Yeah.
And I'm a little lost, I'll be honest.
Okay, so think about a set of actions like
Okay.
our translations and rotations.
Right.
Imagine like a robot that can move one step forward or turn 90 degrees.
Okay. Yeah.
A free group is like a program for that robot
Okay.
that lets you combine those moves in tons of different ways.
And so the robot can just like wander around.
Yeah, and it creates these unique paths,
Mm.
and it never like accidentally cancels out its steps.
Okay, I think I see.
So it's like a robot with free will, just making all these complex moves.
And by using these free groups, you can actually create these
Yes, yeah,
paradoxical sets.
that's exactly right.
Hmm.
Okay, so it's like,
Each point gets its own little set of instructions
yeah,
based on the free group
okay.
telling it how to move and where to go in the grand scheme of things.
But this all sounds like mathematical sleight of hand or something.
Well, it's not quite a loophole, but it does rely on a
Yeah.
pretty powerful principle in math.
Okay.
It's called the Axiom of Choice.
Oh yeah, the Axiom of Choice.
Yeah, have you heard of this?
I've heard of it, but explain it like I'm 5.
Okay, so basically it says you can make...
Infinitely many choices at the same time.
So it's like being able to pick one apple
Right.
out of every basket in an orchard
Yeah.
that like goes on forever.
That's a great way to think about it.
Wow, and that's necessary for creating these strange sets.
Absolutely.
It's a powerful idea.
Yeah, and it's been debated by mathematicians for decades.
Some people think it's too powerful,
Mm.
and others think it's essential.
It's one of those fundamental assumptions
Yeah.
that can lead to really mind-blowing results.
Okay, so just to make sure I'm following,
Sure.
we're using these free groups
Yes.
to create sets of points that we can't really measure in the normal way.
Right.
And we're using the axiom of choice,
Yep.
which lets us make an infinite number of choices at once.
Exactly.
And all of that together, it's saying that
Well, it's suggesting that maybe, just maybe, you can double something.
Double it.
Just by rearranging its parts. Wow.
But, we're talking about mathematical sets here.
Right, not actual apples.
Yeah, we can't just double our food supply by cutting things differently.
Right. It's not breaking the laws of physics.
No,
It's
more about exploring the limits of mathematical logic.
Yeah, and what's really possible, even if it seems impossible.
Absolutely.
It's pretty amazing.
It is pretty amazing.
Yeah.
Welcome back. I hope you've had a chance to digest all that.
Yeah.
Because we're going to take a closer look at how this paradox actually works in practice.
Okay, I'm ready for it.
All right. So remember we talked about selecting certain points.
Yeah.
And then applying those free group actions to them.
Right. It's starting to feel like we're building this very specific and very strange mathematical puzzle.
That's a great way to think about it. Imagine like a jigsaw puzzle.
Okay.
Where each piece is a point on a plane.
Mm-hmm. But instead of matching shapes, we're matching actions.
Ooh. Okay.
So each piece fits together based on these translations and rotations.
So it's not about how they look.
Whoa.
It's about how they've been moved.
Exactly. And just like a regular puzzle, all the pieces need to fit together perfectly. No overlaps, no gaps.
Right.
And this is where the whole unmeasurable thing comes in.
Okay, yeah. So walk me through this.
Sure.
How do we actually make these pieces and then put them back together to get, two copies?
Okay, so let's start by picking two specific actions for our free group.
Oh yeah.
So we'll use a rotation around a fixed point and a translation.
So like spinning a coin and then sliding it across the table.
That's a perfect analogy.
Okay, cool.
But there's a little catch.
Oh, there's always a catch.
The angle of rotation, it can't be just any angle. It has to be what mathematicians call an irrational multiple of pi.
Okay. I'm going to trust you on the math here.
Okay.
But what's so special about an irrational angle?
Well, it ensures that the rotation, when you do it over and over, it never brings you back to the exact starting point.
So it's like an endless spiral.
Exactly. It creates this infinite spiraling path,
which is important for the paradox.
It's absolutely crucial.
Okay, so we've got our robot.
Yeah.
And it's on this never-ending spiral across the plane.
Now imagine we pick a starting point and we apply every possible combination of these two actions to it. Spinning it, sliding it, spinning it twice, then sliding it 3 times. Okay, you get the idea.
Yeah, all the combinations.
And this creates a whole collection of points, all related to that original starting point. Oh. And we call that an orbit.
So each point in the orbit is like a snapshot of where the robot was.
Yes. That's a great way to visualize it.
After a specific set of moves.
Exactly.
Okay.
And because our rotation never repeats, thanks to that irrational angle, each point in the orbit is unique. There's no overlap.
Okay, so now comes the tricky part, right?
Now comes the really clever part.
Okay, hit me.
We take this orbit and we divide it into pieces based on the last action that was performed to reach each point.
So one piece might be all the points that were last spun.
Yes.
And another piece is all the points that were last slid.
Exactly.
Yeah.
Now are you ready for the crazy part?
I think so. Lay it on me.
Okay, so if we apply the inverse of the last action to each piece, we end up with 2 complete copies of the original orbit.
Wait, hold on. What do you mean inverse action?
So think of it like hitting the undo button.
Okay.
If the last action was rotating a point clockwise, the inverse would be rotating it counterclockwise.
Okay.
By the same angle.
Got it.
And if the last action was sliding the point to the right, the inverse would be sliding it to the left by the same distance.
If you call the points that were spun, we unspin them, and we get a whole new copy of the orbit.
That's right.
And we do the same thing for the slid points.
Exactly.
That's insane. It feels like we're cheating somehow.
Well, it's mind-boggling, but it's not cheating.
Oh, okay.
Remember, we're not creating any new points. We're just rearranging the existing points in a way that completely changes how we see their size.
It's like taking apart a clock and putting it back together and ending up with 2 clocks.
Exactly. The pieces are all still there,
right?
But but somehow we've doubled the time.
It's amazing. The Sierpinski-Mazurkiewicz Paradox. It's showing us that our ideas about area and measurement, they kind of break down.
They don't quite work the same way.
When we start dealing with these infinite sets.
It challenges our basic intuition about how things should work.
I'm still trying to wrap my head around this idea that you can double something without adding anything new.
It's a tough one to grasp.
Yeah. But it's so cool.
It is really cool.
It makes you think about what's possible, you know?
Yeah, it opens up a whole new world of possibilities.
But we've been so focused on the mechanics of this.
Yeah.
I'm curious to hear your thoughts on what it all means, you know, on a deeper level.
That's a great question, and it's what makes this paradox so fascinating. You know, it's not just a mathematical curiosity.
Right.
It has philosophical implications as well.
Let's dive into that when we come back for the final part of our deep dive.
Sounds good.
Welcome back to the deep dive. We've been talking about this Sierpinski-Mazurkiewicz paradox.
Yeah.
And you know, I'm still kind of stuck on this idea that you can double something without actually adding anything new.
It's a strange one.
It really is.
For sure.
But beyond the crazy math, what does it all mean? Like, what are the bigger implications here?
That's the thing about paradoxes, isn't it?
Yeah.
They really make you question your assumptions. You know, the things you think are fundamental.
Right.
And the Sierpinski-Mazurkiewicz paradox, it does that.
Yeah.
It's not just some mathematical trick. It's a philosophical challenge. It's asking us, like, what do we really mean when we talk about size and measurement?
I think that's a good point. We're so used to, you know, our everyday experience with things, you know, finite objects.
Finite, yeah.
And then when you bring in infinity.
Yeah, infinity throws a wrench in the whole thing.
It just breaks our brains.
It does. It really does.
So this paradox is really showing us that.
Well, it's highlighting this tension between our intuition about the world, you know, how we think things should work.
Yeah.
And the power of abstract math.
Yeah, because math can model the world, but it can also lead to conclusions that seem
conclusions that seem impossible.
Yeah, impossible if you try to picture them.
Yeah, in the real world.
Right.
Yeah.
But that doesn't mean those conclusions are wrong.
No, not necessarily.
It's more about expanding our understanding of what's
expanding our understanding of what's logically possible.
Yeah, even if it seems counterintuitive.
Even if it bends our minds a little bit.
Yeah, exactly.
So that's the beauty of it.
So the Sierpinski-Mazurkiewicz paradox, it's telling us that
it's showing us that
logic can sometimes lead to conclusions that seem completely bizarre.
Bizarre, but still consistent.
Yeah.
You know, within the rules of math.
It's like math has its own set of rules that are different from
the rules of the physical world.
Yeah, the rules of reality.
And that's what makes it so exciting to explore.
I know, it's like we're peeking into this other universe.
This universe of pure mathematics.
Yeah, where things work differently.
Where the impossible can become possible.
So for our listeners who are maybe feeling a little uneasy right now about all this.
A little bit of mathematical vertigo.
Yeah, what would you say is the most important thing?
I think the key takeaway is this. Don't be afraid to question your assumptions, even the ones that seem really, really basic.
Like what?
Like our ideas about size, measurement, what's possible, what's not possible.
Because the Sierpinski-Mazurkiewicz paradox it's a good example of
a perfect example
how our intuition can be wrong.
Yeah, how our intuition can lead us astray.
It's a reminder that the world of math, it's full of
surprises.
Yeah, surprises and paradoxes.
And embracing those mysteries, it can actually lead us to a deeper understanding.
A deeper understanding
of the universe, you know, both the one we can see and the one we can only imagine.
I love that.
It's a beautiful thing.
So this deep dive has definitely, opened up my mind a bit.
I'm glad to hear it.
And I hope it's done the same for our listeners.
Me too.
And if you want to learn more about this, we've got some links in the show notes.
Check those out. There's some fascinating stuff there.
To some really interesting articles and resources.
Yeah, dive in, explore.
Yeah. And then remember, the next time someone tells you something's impossible.
Right.
Oh, in the world of math.
Yeah.
Maybe it's not.
The only limit is our imagination.
That's a good way to put it.
Keep exploring. Keep questioning.
Keep diving deep.
That's what it's all about.
Thanks for joining us.
It's been a pleasure.